to St. Joseph University in Tanzania. Paper 2 is designed for students who are preparing themselves for the coming national examination. Therefore, I'll pass through different questions from different topics of paper 2. Yes. Join me now up to the end of this program, and finally enjoy our lesson. You're welcome. This paper 2 has 6 questions. Question number 1 from fluid dynamics topic. So the question is, A Roman 1. A Roman 1 party. A Roman 1. What do air bubbles, or why do air bubbles in water rise up? The question is asking why bubbles in air in water rises. So to answer this question, you must consider the following. First, water is free, and it is a viscous fluid, because all the fluids in nature they are viscous. So bubble is a spherical shape, is of a spherical shape. That means it can flow in viscous fluid like other solid spherical body. So why it rises instead of sinking? As we know, all solid spherical body sinks. Consider this so-called terminal velocity. Vt equals to 2g r square bracket density of the solid minus density of the fluid over 9 eta. This is the density of the solid which is flowing through the viscous, and this is the density of a viscous fluid. Therefore, for air bubble, its density is less than the density of water. So what will happen if we substitute in the formula? Vt will be negative, because density of air bubble minus density of water is negative. Then the velocity will be negative. Negative, instead of going down the fluid, it will be going up. It means to be in the opposite direction. Instead of sinking, will be rising. So the reason why air bubble rises in water, it is because it has got negative density, a negative terminal velocity. And this negative terminal velocity is due to the density of air bubble as a spherical body to be less than the density of the fluid in which the bubble is flowing. Roman 2, a sphere is dropped under gravity through a fluid of viscosity eta, taking average acceleration as half the initial acceleration, show that the time taken to attain terminal velocity is independent of the fluid density. So in Roman 2, we supposed to show that the time it's taken by the body that is moving in viscous fluid, starting from the surface to the inner part, is independent of the density of the fluid. So this is the fluid is having a density sigma. This is the spherical body with a density rho. Then we are supposed to show that the time it takes from the moment it is released on the surface of the fluid to the moment it attains the terminal velocity. That means it start moving with a constant velocity. This time taken between these 2 points does not depend on the density of the fluid. That is what you are supposed to show. Okay, to start with this question, first we know that when a spherical body is placed on the surface or is released from rest on the viscous fluid, there are several forces that will act on it. First force is the drag force, the other one is the buoyant force, or we say upthrust, and also there is a weight of this spherical body. So according to Newton's law, if the direction of motion is downward, then this weight, if you minus with the opposing force, which is drag force plus upthrust, is equal to net force. And the net force is mass times the acceleration. But because just an initial point, we say initial acceleration. But this drag force, according to Stokes' law, this drag force, initially, drag force is equal to 0. Initially. Why it is 0? Because this drag force depends on the velocity. So the moment you release it on the surface, velocity is 0 because it is starting from rest. Then everything becomes 0. So the weight minus upthrust is equal to mass times the initial acceleration. Then initial acceleration will be equal to weight minus upthrust divided by mass. Then what is the upthrust? Upthrust, this one, upthrust according to Archimedes' principle, this is equal to the weight of fluid dispersed. So it is the density of the fluid times the volume of liquid dispersed times G divided by mass of the solid. But the volume of this fluid dispersed is almost equal to the volume of the immersed body, which is a sphere. So this is equal to mass times G minus density. Here the density of this sphere we don't have, but we the volume of the sphere, we can write this volume of the sphere equals to either mass of the sphere divided by its density, then it times G over M. So M and M cancel out. What will be the remaining it is G bracket 1 minus density of the fluid over density of the solid. If you like, you can just write G bracket density of the solid minus density of the fluid over density of the solid. That is the initial acceleration. We call it equation number 1. Also, if this body now gets to the point, this one, so at the point of attaining maximum velocity or attaining terminal velocity, the equation will be different, because now this velocity is not 0, it is Vt. So you can write the same equation, mg minus fd plus mu equals to ma. But this time a is a final acceleration. It's different from the initial. So only substituting this, you have mg minus bracket fd plus u equals to ma. Fine. But this af is equal to 0. Y constant velocity. This moment here, the velocity is constant. So what will happen? It means mg minus mu equals to fd. As I said, this is equal to m. This is the upthrust or upthrust. Upthrust, it's the same as density of the fluid times the volume of the fluid. Volume, which is the mass over density times g, and this one it is 6 pi eta r v terminal. So again, you can make v terminal the subject, which is equal to m g bracket 1 minus sigma over density divided by 6 pi eta r. So again, we don't have the mass. So the mass in this case mass equals to density times volume. What is the volume of a sphere? It is 4 over 3 pi r cube. If we substitute it there, you have terminal velocity equals to 2g r square bracket density of the solid, density of fluid over 9 eta. So this is the second equation. Again, remember the question wants us to find the time we've taken to move from A to B. Then from linear motion equation, equation 1, final velocity is equal to initial velocity plus acceleration times t, which is time. For this case, our final velocity is terminal velocity. Initial it is 0 because started from rest. A, it is the average acceleration. Why average? Because we are having two acceleration. Acceleration initially and the acceleration final, which is 0. So times t. So what is A, B? According to this problem, we have been told that the average acceleration is just half of the initial. But even if we could not be given, average acceleration is taken by initial plus final acceleration divided by 2. So this is equal to 0. So 0 plus this one is equal to I over 2. So even if you are not given, the average acceleration is half of the initial acceleration because the final acceleration is 0. So terminal velocity now equals to I over 2. What is terminal velocity? Terminal velocity is this equation. 2g square bracket density of the solid divided by 9 eta. Average acceleration is, that is equation number 1, this one. So it is again g bracket density of solid, density of the fluid over 2 density of the solid. So g and the g cancel out, this difference and that difference cancel out. What will remain? Oh, that means is equal to 2 times t, so there is a t there. So to make t the subject, t will be equal to 2 times 2, it is 4 log r square over, down here there is 9 eta. So this will be the time taken by the solid to move from point A to point B. So in this time, independent of the density of the fluid, you go and look in this formula of the time. Is there any density of fluid? That means eta. There is no eta. Therefore, you conclude the time to attain terminal velocity is independent of the time of the fluid in which this solid sphere is flowing. So does not depend on the density. We move to second question, which is B, Roman 1. Why are oils of different viscosity used in automobiles in different seasons? To respond to this question, first of all, you must know that seasons are categorized depending on the temperature of the, we say weather temperature or temperature conditions. Therefore, how temperature now affects the viscosity? Viscosity is affected by temperature. As temperature increases, viscosity decreases. Therefore, because the viscosity or the oil with the viscosity X is suitable during the winter, might not be suitable during the summer because its viscosity will be changed. For that reason, different oils are used during different seasons because of this effect of temperature to the viscosity of the oil. Roman 2, this is the calculation. B Roman 2, we have been given a metal plate, and between there is the fluid. This is 0.01 kilogram. So this is the film of liquid. So it is a liquid film. The metal plate area, we have been given the area equals to 0.1 meter square. The thickness of this fluid, X equals to 0.3 millimeters. And also we are given the constant velocity of which this metal is moving when this mass is released to be 0.085 meters per second. So what is the question? The question is find the coefficient of viscosity of the liquid when it is. We may assume that the pulley is massless and frictionless. So when this mass is released, then the tension T, which is equals to the tension T there, will be pulling this metal plate. And the results causing a tangential force. So from Italian fluid force, tangential force is equal to a magnitude of viscosity coefficients eta, area of the plate, times the velocity gradient. Therefore, we are looking for this, but what is our force in this case? Force is equal to tension. So tension equals to eta A velocity gradient dx. And therefore, this eta will be equal to force, distance or thickness of the fluid over area times the velocity. But this force is equal to mg. Why? Because if this mass is going down, what will happen is the net force mg minus t is supposed to be ma, which is the acceleration. But we are told that the system is going with the constant velocity. For a constant velocity, this acceleration is equal to 0, making m equal to 0. I mean, mg minus t is equal to 0. Then t is equal to mg. So substituting it there, eta will be equal to dx over area times velocity change. So we have everything, we can find what is eta. So eta equals to m is 0.01, g is 9.8 times dx, that is the thickness, 0.3 times 10 raised to 3 into meter, divided by area, which is 0.1 meter square, times the velocity, which is 0.085. On calculating, you can calculate using your calculator to get the viscosity equals to 0.00346. Either you can put into Newton second per meter square or Pascal second. 0.00346 Pascal second. We move to another question in Roman 3. Roman 3, we're given 3 capillaries of the same length, but internal D, 3R, 4R, and 5R connected in a series, and the liquid is flowing through them. First, we have 3 pipes. Of the same length. This is L, this is L, this is L. But this is having R radius, 4R radius, 5R radius. And the liquid is allowed to flow through them. What are the more information? Under streamline conditions, so the flow is streamlined. If the pressure across the third capillary is, so if this is the point A, B, C, D, that is the third third capillary, then the pressure between, which is equal to PC minus PD, is given to be 8.1 millimeter of liquid, which is flowing in. So what is the question? Find the pressure across the first capillary. So we are looking for the pressure across the first capillary. The property for streamline flow, then the rate of fluid flow in the first pipe of capillary is the same as the rate of fluid flow in the second as well as the third. So from Q1 equals to Q2 equals to Q3, which is the rate of flow or volume per unit time. Then because we have been given the information about this and we are looking for this, then pi r out. The first for change in the pressure 1 divided by 8 eta L, length is the same, equals to pi r 2 4 change in pressure across the second capillary divided by 8 viscosity coefficient times L equals 2 pi R Ferrari for change in pressure Ferrari over 8 eta L. So equating the first and the third, you will have R1 for change in pressure 1 divided 8 eta L equals to pi R Ferrari change in pressure Ferrari divided by 8 eta L. So you can cancel this one pi, then you get pressure across the first capillary equals to R Ferrari over 1 bracket exponent 4 times the pressure across the third. So everything is given. So the pressure across the first capillary equals to R Ferrari is equal to 5 R, while R1 is Ferrari R exponent 4, and the change in third capillary is 8.1 millimeter of liquid. If you calculate, you will get R and R cancel out, so it is just 5 over 3 exponent 4 times 8.1, which on calculating you will get 62 point 5 of liquid. You can check on your calculator to see if you are getting this output. Part C. Part C, the question is, part C, Roman 1. The question is, the accumulation of snow on an aeroplane wing may reduce the lift. Explain why. To explain why the lift can be reduced due to the accumulation of snow on the wing, first of all, you must know how lift is generated from the wing of the plane. Wing of the plane have a structure of aerofoil. So that air can pass a long length above compared to the air passing below. So because they have to reach this point at the same time, the velocity upper must be greater than the velocity below. So then, because of difference in this velocity, and the pressure also will be difference, the difference in the pressure will generate a lift force up. So what will happen when this wings, the snow accumulates on the top of the wing? The first thing that will happen is the destruction of the aerofoil structure of the wing. If it is distracted by any means, will affect the lifting force. So to respond that to this question that the lift force may be reduced due to the destruction of aerofoil structure of the wing. Okay, so the accumulation of the snow will destruct the aerofoil structure of the aeroplane wing. As a result, this lifting force will be reduced. Roman 2, airflow over the flows over the upper surface of the wings of a jet plane at speed of. So that Roman 2 is similar to this one. In the upper, it is meter per second, while below it is 30 meters per second. If the total wing area equals to 50 meters per second square, then the question is determine the lifting force. So lifting force is given by change in pressure times area of the wing. But this change in pressure is obtained from the Bernoulli's principle. For Bernoulli's principle, if this is the pressure below and this is the pressure above or upper, therefore from Bernoulli's, because this is the very thin, we assume it is the horizontal, there is no elevation, or the elevation is negligible, then the pressure upper plus half density velocity upper square equals to pressure below plus half density velocity below square. If you separate, this go to this side and this one, this go to this side, this go to that point, you have P below minus P upper equals to a half rho bracket velocity upper square minus velocity below square. This is the change in pressure. So change in pressure equals to a half density bracket velocity below, upper square minus the velocity below square. So to get the lift, you substitute, you multiply by area. Therefore, the lift force is equal to a half density area bracket velocity upper square minus the velocity below square. If you substitute those values, a half the density of air, because the plane or the fluid which is flowing over and below the wings is air. We have been given the velocity of air as 1.29 kilogram per meter square. So area is 50, then this is the 340 square minus 230 square. you can calculate from your calculator and give the output there. Roman 3. Water flows steadily along the horizontal pipe at the rate of. So, Roman 3, we have given the rate of water flow to be 8 times 10 raised the meter cube raised negative 3 meter cube per second. Cross section area to be 40 times 10 is negative 4 meters square. Find the total pressure if static pressure. So P static equals to 3 times 10 exponent 4 Pascal. So we are looking for the total pressure. To respond to this question, first of all, for horizontal pipe, the total pressure is equal to the static plus dynamic pressure, which is a half density of fluid velocity squared. So we have this static, we don't have velocity, but you have been given the rate of fluid flow and the area. So we know that this is equal to velocity times area. So velocity is equal to Q over area. Area is there, Q is there, so you can find this is 8 times 10 negative 3 over 40 times 10 negative 4. So this you get, you calculate the velocity here, almost 2 meters per second. So you can apply it there and find the total pressure equals to static, which is the 3 times 10 exponent 3 plus a half times the density. What is the density of the fluid? The fluid is water, so this is 1,000 times the velocity square, which is the which is 2 square. So you get the answer for the total pressure. We move to part D. D Roman 1. What is the significance of Reynolds number in the fluid dynamics? Reynolds number, this is a dimensional constant or dimensional number which characterize the nature of all fluid flow. That means it can tell whether the flow is streamlined or the flow is turbulent. So the significance is used to characterize the nature of flow. Roman 2, the flow rate of water from a pipe of diameter. So Roman 2, we have a diameter equals to 1.5. This is the centimeter, and the Q, which is the 50 times 10 exponent 6 meter cube per second. what is the nature of this flow? So what is the nature? It means characterize the type of flow, whether it is streamline or turbulent flow. First of all, as I said, the significance of Reynolds number is to characterize the nature of flow by considering the number, whether the Reynolds number is less than 3,000 or it is above 3,000. So from Reynolds number equals to density, velocity times diameter divided by viscosity of liquid. We can calculate this number, and from the number we can conclude whether the nature is turbulent or streamline. So we have this density because this is the water. We don't have velocity, we have diameter. But also we know the rate is equal to velocity times the area. But for the pipe, area it is pi d square over 4. So from this we can find this velocity is equal to 4q over pi d square. If you plug in the question, this will be density 4q over eta pi d. That means the other d will cancel with one of the d square here. You remain with this one. So here I can substitute and get the number. What is the viscosity of water? From the first page, viscosity of water 0.01. So the density is 1,000 times 4 times 50, 10 negative 6 over eta, which is 0.01 times 3.14, then it times the diameter, which is 1.25 times 10 exponent negative 2. You get this number here. If this number that you're going to get is less than 1,000, then this flow is streamline. If it is above, it will be turbulent. We move to question number 2. Two part A, Roman 1. What is the difference between interference and diffraction? Interference and diffraction, of course, diffraction is due to interference, but the only difference between interference and diffraction is that for interference is happening due to the superposition of two coherent waves coming from the same source, or we say two waves coming from two coherent source of wave. That means you have one slit there, you have another slit, then this two waves will meet somewhere and interfere, either constructively or destructively. That is the interference. But for the diffraction is a superposition of two wavelets coming from different points of the same wavefront. That means you have a wavefront like this one. So there is the wavelet generated from that point and from this point. Then on the progress, they interfere here either constructively or destructive. So the fringe formed here is due to deflection. So you can see that all involve the interfere also opposition of waves, but they are different in their origination. This is the originate from the same wave front, and they meet there and they interfere either constructive or destructive. But for interference, we have the slits, but or from two coherent source. Another difference that you can add there is the nature of fringe that are formed. For interference fringe, first of all, there are many and they are equally spaced. That means fringe separation is constant. But for deflection, the fringe keep on diminishing. That means even their intensity, they are not constant. But in interference, even intensity is constant. But in deflection, the intensity is not constant. Another thing that you can add in the part of deflection and is even the number of fringes formed. In interference, there are many fringes that are formed, but in the deflection, only a few fringes can be formed. If I move to Roman 2, define the path difference. Path difference, just the difference in the two distance taken by what? By two waves or two rays. For example, if this is ray 1, this is ray 2, then they meet here. If this is the length 1, this is the length 2, then the path difference is equal to L2 minus L1. So just the difference in the path taken by two rays of wave or two waves. Roman 3, a light whose wavelength is 6 times 10 exponent negative 8 negative 7 meters is used in Young's double slit experiment, whose slit separation is 2 millimeters and the distance from the screen is 20 centimeters. When the transparent material of thickness 0.5 millimeter is mounted across the path of one source, there is a fringe shift of 0.5. Find the refractive index of the medium. So this is the first switch, this is the second, and this is the screen. So there is a ray from that switch 1, and there is a ray from this switch 2. They meet there. After meeting, they interfere. So it means the length here is the fringe size. So on replacing this Y fringe is a normal fringe without any transparent material placed. But on placing a transparent material, that means because the rate of O due to diffraction, this path will increase. So after increasing, it means instead of interfering here, the two waves can interfere somewhere else. So again, this is the y dash. So we have been given that the change, the fringe shift y m dash minus y m equals to 0.5 millimeters, or change in y equals to this one. So first of all, if this is d, we know that what is y? Y m is equal to lambda d over this one. So what will happen? This is it because of the normal normal interference without a transparent material. But when you put transparent material, y m will change. Instead of having this one, will be just d over small d bracket any lambda plus mu, which is the refractive index, minus 1 times the thickness. That will be the m dash. So because that will increase. Or if I write this is p, this is the p dash. Initially, the fringe separation here, which is the x, changing x, or path difference changing x, was given by sp minus s2p minus sc1p. But if you introduce this sp, this path will be increased. So now path difference will be equal to S2P minus S1P plus the increase in the path times T. So if you open up and you come up and with this one. That's where this equation is coming from. So now, if you take the difference of these two, change in y, you take d over small d lambda, this is any lambda, plus refractive index of the material minus 1 times t minus d lambda n over d, you end up having d over d bracket mu minus 1 times t. So the shift in fringe equals to this one. So the question is, find the refractive index. We are looking for this one. So it is refractive index will be equal to shift times d over B times T, then plus 1. So everything you have, the shift it is 0.5 millimeters, straight it is 2 millimeters, D is 20 centimeters, so you can put 200 millimeters, and the thickness shift is 5 centimeter, but thickness is 0.5 millimeters. So millimeter cancel with millimeter. It's 10 over 100. Is it? This is equal to 10 Is it 10 over 10? Two millimeters separation, 20 centimeter. I'm getting almost 1.0. This is 10, but you can try on your calculator to find what will be the output. So this will be plus 1. So I've forgotten it, plus 1 here. So this is 10. This one is 100 plus 1. So is equal to 1.1. So refractive index is 1.1. B, Roman 1. An air wedge film is formed by placing aluminum foil between two glass slides at a distance of 75 millimeters from the line of contact of the slide. So you have two slides, 1 and 2. That is it. This is the point of contact. There's a distance of 75 millimeters to the point where this aluminum foil is placed. So the thickness of aluminum, it is T. This is angle theta. When the air wedge is illuminated by light of wavelength, so we have the light of wavelength, which is equal to 5.6 times 10 exponent -7 meter. Interference fringe are produced parallel to the line of contact, which has a separation of. So we have a fringe separation. Let's say one fringe is at this point, the other is there. So the fringe separation it is S there. But if you draw this line, this angle will be the same. That means for parallel line, this angle and this one is the same. What we know from the fringe separation that if this is the separation of fringe, then the distance from there is equal to the half of wavelength. So very important point. Otherwise, you will have to find the total number of fringe formed from this end to the last, and eventually come and find this length there. So the question is calculate the angle of the wedge theta and the thickness of the foil T. So first, from the triangle, tangent of theta equals to opposite over adjacent, which is L. But also this, using the upper triangle, tan of theta is equal to half of wavelength divided by separation. So you can see that this second equation, we have the wavelength and we have the separation. So this is equal to, wavelength is given as 5.6 times 10 negative 7 to separation is, they didn't write separation is 1.2 millimeters, so negative 3. If you divide this one, you get almost 0.000 2, 3, and so on. So that is the tan of theta. You can also find theta by taking the tan inverse of this one. But in radian, because this is the very small, in radian, the angle remains this one. Second part, you are looking for this T. So T is equal to L times tan of theta. So L is 75, tan of theta is this one, 0.00 to 3. So you get your thickness of the foil. C, monochromatic light of wavelength 5.2. Part C, monochromatic light 5.2 times negative 7 meter. Falls normally on a grating which has so G grating equals to 4.0 times 10 exponent 10 exponent 3 lines per centimeter. Roman 1. What is the largest order of spectrum that can be visible? So this is diffraction. Maximum order from separation times sine of the angular displacement equals to order of the separation times the wavelength. To get a maximum order which will be visible, then this sine of angle should be maximum. And we know that sine of angle is maximum when it is equal to 1 for maximum. Therefore, D equals to any lambda. So N is equal to D divided by lambda. So the question is, we don't have this value of D, but we know how D is related with the grating. But D is equal to 1 of the grating. If I substitute, N will be equal to 1 of G times lambda. So now everything I have, this is 1, G, which is the getting it is the 4 times fillet lines per centimeter, but if you want to per meter, this is times 5 times 5.2 times 10 negative 7. On a calculation, you get 4.8 something there. Then there's a decimal point. So which one you are going to take? Some people, some students do mistakes here by estimating, because they see number of order, it is just a natural number, not a decimal point. You cannot have order and a half or order point. So some students make mistake here to approximate into 5. Take the way it is. So the maximum number is the 4 number of order is the 4. That is the one approach. The other approach, you can use this equation by checking. You start with d sine of theta 1 equals to any, or you start with the 1 lambda, you go 2, you go any 3, you go any 4 until you get the answer sign error or impossible. Then you end up a previous number. So it can take you time, but still you can get the same answer for. Roman 2, find angular separation between the third and the fourth order image. So again, from d sin theta equals to any lambda for 4 order, then this will be 4, this will be 4. So d, because we are looking for the angle, sine of theta 4 equals to 4 lambda. Dividing by d, theta 4 is equal to sine inverse of 4 lambda divided by d. As I said, we don't have d, but we have g, so this will be sine inverse of 4 lambda g. But your g should be per meter, so that it can cancel with the meter from the wavelength. So you get the first angle on my calculations. I'm not sure about 50 something, 56 .3 degree. Then you repeat for the third order, d sine of theta phi equals to phi lambda. Again, you find for theta phi, which according to my calculations are 38.6. After getting the two angles for our angular displacement for third and fourth order, then the angular separation equals to theta 4 minus theta 3, 56.3 minus 38.6 you get the answer there. That will be the angular separation. D Roman 1. The diameter of M and N plus M plus 10 bright fringes formed by convex surface of a long focus plano convex lens resting on a plain glass surface as 0.14. So we have the diameter of M equals to 0.14 millimeters. This centimeters. And we have dm plus equals to 0.86 centimeter. When the space between the lens and the plain glass is filled with the liquid, the diameter of another, so we have another dq. This is the with the liquid between the glass, between the lens and the glass. Q diameter is equal to 0.3 centimeter, and the D of Q plus 10 equals to 0.77 centimeter. What is the question? The question is, what is the refractive index of the liquid that is placed between the plate? That means if this is the curved lens and this is the, so there is a fluid placed in between here. So the image of this plano lens it changed. That means those the circular fringe which are formed if you go from the top on the glass will shift. So first of all, for bright fringe in Newton's ring, diameter d square is equal to 4 bracket of 4r lambda bracket, which is yes, you can write either any minus a half, this one, or you can just write any plus a half if you are starting from 0. If you start from 1, that is the formula. So if you simplify, this will be 2r lambda bracket 2n minus 1. Therefore, for dm, this is square equals to 2r lambda. This will be 2m minus 1. Here we have been given 2m is equal to 0.4. So 0.14 square equals to 2r lambda bracket 2m minus 1. After that, you go for the second, when it is dm plus 10 square, the answer is equal to 2r lambda bracket Now it is 2m plus 10 bracket minus 1. So I can simplify this. This is 0.86 square equals to 2r lambda bracket 2m. I guess will be plus 19 if I don't mistake. So this will be the second equation. If this is the first, so subtract the second from the first from the second. So 0.86 square minus 0.14 square equals to 2r. This is 2m plus 19 minus 2r lambda 2m minus 1. So if you minus this, you get 2r lambda, then it times 2m plus 38 r lambda minus 2r lambda times m plus 1. So this and this one will cancel out, this and this one, or this one will be 2r lambda. So you find that this is equal to 40 r lambda. So you can make r lambda subject by taking 0.86 square minus 0.1 square divided by 40. A quick calculator can be, you can quickly 0.86 square minus 0.14 square equals to this one divided by 14. So you can get r lambda equals to 0.018. That is the third equation. You do the same to the case when the liquid is pressed. When the liquid is pressed, we have seen that dq, where is the dq? This one. So 0.23 here with the liquid. 0.2 minus is equal to 2r lambda bracket 2q minus 1, and another one which is 0.77 square equals to, but something which is important, this lambda is not the same as lambda in before. This is the lambda dash, where the lambda dash is equal to the lambda in air divided by effective index of the liquid, because the wavelength in the liquid normally decreases. So here, be careful when you are writing the second equation. So this is the lambda dash bracket 2 again q plus 10 minus 1. If you separate, you will have the same equation, 0.2 is, if you subtract the second equation, (0.77 square minus 0.23 square equals to), if we subtract this, you almost end up with the same expression, r lambda, this one, but this is lambda dash. As I said, you have now to substitute this lambda dash. So you'll be having 0.77 square minus 0.23 square equals to 40 r lambda over refractive index. So if you want to make refractive index the subject, this will be equal to 40 r lambda divided by 0.77 square minus 0.23 square. As I said, our lambda, r lambda is equal to this one. So this will be 40 times 0.018 over 0.77 square minus 0.23 square. You get your answer there. So you're getting the answer equals to 1.431 almost 7. So the refractive index of the liquid, it is 1.43. That is a required refractive index. If we move to the next question, Roman 2. Roman 2, the question is the wavelength of light emitted by hydrogen in a star is found to be shifted by, so there is a wavelength of light emitted by a star which is 63 angstrom, or equals to 63 times 10 raised meter, is shifted to 15 angle, which is equal to 15 times 10 exponent negative 10 meter. Then estimate the speed with which the star is receding from the Earth. So if we let u be the speed of the star, therefore the shift in wavelength due to red shift or blue shift is equal to the velocity of the star, which is u, times the wavelength of the light emitted by the star divided by the speed of light. So we are looking for this speed of the star. This will be equal to shift of in the wavelength times the speed of light divided by wavelength of light, which this is equal to the shift is 15, speed of light is 3 times 10 exponent 8, and the wavelength is 65.63. So the angstrom here and the angstrom here cancel out. That's why I didn't include. So you get the speed of light. Not sure if I have the speed of light to be 6.86 times 10 is the 5 meter. So the receding star will be moving at this speed. I move to the last part E. Roman 1. A parallel beam of unpolarized light in air is incident at angle of this one. So we have the polarizing angle theta P equals to 54.5 degree. The reflected beam is completely linear polarized. Then Roman 1. This is E Roman 1. What is the refractive index of the glass? This is normal, this is the incident, this is the reflected line. If it is linearly polarized, then this is the angle of incidence, which is the theta, will be the angle of incidence will be the angle of polarized incident, and this one, of course, only part of the light is polarized. It means the other one will be transmitted. The transmitted will be a little bit reflected. And this is angle of reflection. So from Brewster's angle, tan of theta P is equal to reflective index of the material. So what I need only is to find the tan of the given angle, which is 54.5 on a calculator. You get 1.4045. So the reflective index approximately 1.4. Roman 2. What is the angle of reflection of the transmitted beam? What is the angle of reflection? This one. For complete of plane polarized, the angle of polarization plus the reflection is equal to 90 degree. This is the case, minus angle of polarization. So 90 minus 54.80 degree, you get almost 38.2. 90 minus 44.5, you get almost 35.5. So this is the angle of refraction for transmitted ray. Question number 3. A, Roman 1, state the assumption of kinetic theory of gases. Of course, those are the assumptions. Assumption number 1, that is the volume of the molecules is negligible as compared to the volume of container. Assumption number 2, that the force, intermolecular force of molecules is negligible except the force of collision between the molecule and the container. Another, that is these molecules that are treated in this spherical body and they obey Newton's law of motion. That means they move in a straight line. And another assumption that you can make in kinetic theory of gases is maybe the effect of course, molecules are moving in random motion. So for you to treat the motion of, you must assume that they are moving in a linear motion. So I think I've mentioned it in a case of Newton's law, that they obey Newton's law. So Roman 2, figure 2, we have been given the figure. With the cork here, we have been given the volume, 3 meter cube, pressure 5 times 10 exponent 4 Pascal, as well as the temperature 50 Kelvin. Here it is 7.2 meter cube, pressure is 2.0 times 10 4 Pascal, and the temperature is 400 Kelvin. Therefore, what is the question? Find the pressure after connecting tap has been opened and the system has reached equilibrium, assuming that A is kept at 250 Kelvin and B is at 400 Kelvin. That means what will be the final pressure if this cork or tap is opened and the temperature of the two containers remain the same. To do that, you can relate NAB, number of moles in the first container, number of moles which is equal to PV over RT. That means AATA. And this NB be equal to PB VB over TB. You can calculate this number of moles and finally get the total number of moles in the system. It is Na plus Nb. You get the answer. The first case, this is before opening. After opening, because this pressure is low compared to this one, some of molecules from this container A will move to container B until the equilibrium is reached. That means the total pressure is the same. Therefore, no more molecule will be moving to container B. So what will be a new number will be N2. So for the N1, here I can calculate because everything I have there, 50 times 10, 4, volume is 3, temperature it is 250 R. This one it is pressure, it is 2, 10, 4, volume is 7.2 over 4R. You get the answer. After opening, again the total number of moles will be Na plus Nb bar. But what is Na this time? Na this time it is the pressure times the volume A over 2 R times 250 temperature, and this one it is P V of B over 400 R, because we are told the pressure, the temperature of the system remains the same. So after getting, we have this VA and VB because the container does not change its volume, but only the pressure we don't know. But the total number before opening and after opening remain the same. So by comparing, you can have P VA over 250 R plus P VB over 400 R equals to the initial one, which I don't know, I didn't calculate it, equals to 5 times 10 exponent 4 times 3 over 250 R plus 2 times 7.2 times 10 raised to 4 over 400 R. So after that, you make P the subject. P the subject will be equal to 5 times 10 exponent 4 times 3 over 250 R plus 2 times 10 exponent 4 times 7.2 over 400 R. This total, it is over 3 to 4 R plus this is 7.2 over 400 R. After that, you can simplify and you get the final pressure of the system. Let me check if I have calculated in my calculator. Yes. To get the pressure equals to 3.2 times 10 exponent 4 Pascal. You can also check R will cancel with the R top. R cancel out. Then if you combine this one, divided by this one, you get this. Romani 3. The mass of hydrogen atom is, so we have mass of hydrogen 3.2 times 10 exponent negative 27 kilogram. Strike fixed wall of area. So we have the area equals to if 10, so we have also the number of molecules. If 10 exponent 23 molecules strike a wall of area 2 centimeter square and angle. So we have this wall. So this is the striking and the rebouncing at angle 50 to the horizontal or to the normal with the velocity v and escaping with the velocity v. So what is the question? I've been given even speed 10 exponent 3 meter per second. So what is the question? Calculate the pressure exerted on the wall. The pressure exerted on the wall. What will be the pressure here? Our pressure is equal to force exerted divided by area or per unit area. And this force is equal to rate of change in linear momentum divided by area. So let us see what is the rate of change. Rate of change in linear momentum is equal to mass of a gas times change in velocity. So first resolve this one into horizontal. This is v cosine of 45, and also the rebound velocity. If we resolve into the horizontal, we'll have this one v cos of theta. So final minus initial, but the final and the initial are in the opposite direction. So I'll get 2 v naught cosine of theta. That is change in P. What will be the change in time? The time normally is equal to 1 of the number of molecules colliding. That means is equal to 1 over t exponent t minus by in time. So in that way, I'll get this is equal to 10 because the any number of molecules was 10 exponent this one. So the time will be negative 3 seconds. So each second this will be hitting the time of impact will be this one. Now, what is missing? Pressure equals to the rate of change, which is twice mass times velocity times cosine of 45, that is change in momentum, divided by time, of course, which is it is n. Is it n? It is 1 over n, and 8 times the area. So everything I have, 2 is there, mass is 3.32 times 10 negative 27, velocity is 10 exponent 3, and the cosine of 45 divide by this is 10 negative 23, and the area is 2 centimeter, which is equal to 2 times 10 negative 4 meter square. On substituting, you get the pressure as 2.335 times 10 exponent 3 Pascal or Newton per meter square. The other question is, that's Roman 4. At what temperature will root mean square speed velocity of hydrogen molecule be doubled if its value at T, or will be doubled of, I think will be double of its value at any TP. So first of all, velocity with temperature, you know that velocity is proportional with the square root of temperature. That is the root mean square. So velocity root mean square at STP, if I call it V1, or at 0 centigrade, if I call it V0, then V0 equals to K under root of T0, and V equals to K under root of T. So taking the ratio, V over V0 equals to T over T0. For T, this will be equal to 275 Kelvin plus theta in Celsius centigrade. While T0, it is 0 plus this one, which is the same as the 273. Then we are told for V to be twice of this one, that means V0 2 over V0, what will be the value of this theta? 273 plus theta divided by 273. If you square both sides, you have 4 times 273 minus 273 equals to theta. So the answer here will be just 3 times 273 equals to theta. 3 times 3 is 9, 21, 6, 60, then 8. So this will be the temperature. So at this temperature, the velocity, the root mean square speed velocity of hydrogen will be doubled. Okay, we move to part B. Part B, Roman 1. When a piece of chalk is put into water, it emits bubbles in all directions. Explaining why. This is because the chalk has got small spaces inside it. And therefore, when they are pressed inside the water, then due to capillarity effect, water tries to penetrate through those spaces or those capillaries. As a result, because the capillaries they are containing air, then they are forced to get out in the form of bubbles. Roman 2. We have been given a figure there is a bubble with radius r kept at P0, and this is changed by increasing its volume. That means the piston is withdrawn until the bubble its radius until the radius is doubled, so it is now 2r. So the new pressure inside the cylinder is P, while inside the bubble is P2 and this is P1. Okay, the questioning is show that the final pressure of the gas in the cylinder is given by. So we are required to show that the final pressure in the cylinder P is equal to bracket P0 over 8 minus 3 gamma over 2r. That is what we are supposed to show. From the information of the question, the piston was slowly drawn out. That means without causing the rise in temperature. So this is the isothermal condition. So in other words, it was the drawn out and isothermal. For isothermal condition, we know that the pressure inside the first bubble times its velocity will be equal to pressure inside the bubble times its volume. But what is this P1 and how do we get the pressure? So from pressure gauge, P1 minus P out is equal to, because these are just soap bubble. For soap bubble, this is the 4 surface tension of a radius of r. So to get P1 is equal to P0 plus 4 gamma over r. Likewise, its volume is equal to 4 over 3 pi r cube. For second, bubble, you do the same. P2 will be equal to P plus 4 gamma over R2. But R2 this time is twice of the R, so it will be R2, which will give us P plus C twice gamma divided by R, and making the volume 2 equals to 4 pi over 3 times R, which is 2R cubed. Or simple expression, you can just this is equal to 8 exponent R. So now substituting these values in the first equation here, the P1, which is equal to P naught plus 4 gamma over R times its volume, which is 4 over 3 pi R cube, equals to P bracket 2 over R, then 4 over 3 pi 2R cube. So all this pi R will cancel out. We'll have P plus 4 gamma over R bracket. Here this is vanishes, this is P plus 2 gamma over R. Then what remain there is just 8. So divide by 8 each side. You will have P naught over 8 plus gamma over 2R equals to P plus 2 gamma over R. Then making P the subjects, this will be P naught over 8 plus gamma over 2R minus 2 gamma over R. This is the P naught over 8. LCM here. I want to take outside the gamma over R. What remains inside is just 2. So it is a 1.5, which is negative. So 1.5 is the same as 3 over 2. So this will be P naught over 8 minus 3 gamma over 2R. Then shown. Move to C. C Roman 1, briefly explain why water wets the glass and the mercury does not. Water wets the glass because the cohesive force between the molecules of water and the glass is larger than the cohesive force of the water molecules, of glass molecules. So for that reason, water is capable to spread, is pulled away from its molecules. But for mercury, it's the opposite. Cohesive force is greater than the adhesive force, therefore they make as small as possible surface area, which is spherical, to retain its position. The next is Roman 2. Calculate the work done against surface tension force in blowing a soap bubble from radius 10 to 20. So the work done always is equal to change in surface area times the surface tension. So for the bubble, this surface tension is the change in area. It means it is area final minus the area initial. Gamma times area final, it is 4 pi 2 square minus 4 pi 1 square. But for the spherical, the top and the inside, so they are having 2 layers. Therefore, each surface is doubled. So this is times 2, this is times 2. So you find that it is gamma times 8 pi bracket 2 square minus R1 square. If you substitute the slope, surface tension of slope is given in the first page. Surface tension of a slope zero point zero to 0.032 times 8 times 3.14. This is 0.1 square, or this is 0.2 square minus 0.1 square. After that, you get your work in June. The next questioning, Roman 2. Let any droplets each of radius r coalesce to form a large drop of radius capital R, assuming the droplets are incompressible and the surface tension and the gamma is the surface tension. Show that the rise in temperature is given by. So we have any drops, then they coalesce to form a bigger one. So the process of forming a bigger drop, heat is or the work done in forming a bigger drop, heat is supplied. Then the result of heat supplied, what will be the rise in temperature. So simply, you must start that the work done in forming the bigger drop equals to the heat emitted. But this heat is equal to mass times specific heat capacity times change in temperature equals to work done, which is equal to change in area times the surface tension. So to find the change in temperature, this is equal to change in area times surface tension over MC. After that, the change in area, this is equal to the area, because area for drops, when they are small in size and when it is big, you find that the area is large for small drops compared to the bigger one. So I'm going to write is equal to number of drops times a single area of one drop minus the area of the bigger drop this times C subextension divided by MC. The number of drop area it is spherical, so pi r outside, bracket it is any r square minus r capital square divided by MC. But what is the mass? The mass of big drop is equal to density times volume. Volume is 4/3 pi r cube. If you substitute it there, you find that the rise in temperature equals to, oh, there is a sigma there, it is 4 pi gamma bracket any r square minus r square divided by 4/3 pi r cube density C. If you simplify this, you find that 4 pi and the 4 pi cancel out, so this will be equal to 3 gamma bracket any r square. If this r cube go there, will be over r cube. Here you are going to have 1 over r. Then here the total outside will be density times C. Also, from mass conservation, the total mass of the small drops is equal to the total mass of the large drop. So mass, which is density times volume initial, equals to density times volume final. But because density is the same, sometimes we say for drop, volume is observed. Initial total volume is equal to final total volume. So now, the number of drop times the volume of each drop pi r cube will be equal to the volume of a bigger drop. So r cube is equal to any times r small cube. So you take this relation, you come and substitute here. So the rise in temperature this time will be equal to the Fourier substitution over density times specific heat capacity. If you substitute any r small, then you remain with the r minus 1 over r. And this is the required expression. Yes, that is the required expression. D. Two spherical soap bubbles are combined. If the change in volume of the contained air A is a change in the total surface area, show that 3p AV plus 4a 3 PAV plus 4 A gamma equals to 0. So these are the spherical soap bubble, which are two. That means one sphere there, R1, another sphere there, R2. They are combined to form a bigger sphere there, R3. So this is the pressure 1, this is the pressure 2 inside, this is the pressure 3. And the outside there is atmospheric pressure, atmospheric pressure, atmospheric pressure. Then we are required to show that this V being the change in volume and A being the change in area. So to start with this one, first of all, if we assume isothermal, then P1 V1 plus P2 V2 is equal to P3 V3. But how do we get this P1 and P2 and P3? We are using the gauge pressure. So this P1 from here, P1 minus PA is equal to 4 gamma over radius 1. So we can apply the same concept as we did before. So this P1 will be equal to PA plus 4 gamma over R1 times its volume 1, which is 4 over 3 pi R1 cube. The second also will be equal to PA plus 4 gamma over R2 times its volume, which is 4 over 3 pi R2 cube. And this is equal to PA plus 4 gamma over R3 bracket times its volume, which is 4 over 3 pi R3 cube. So enter this inside the bracket, then you group all the one with P in one side and the other with the gamma in the other side. So if I take this times this one, I'll have PA times 4 over 3, then pi R cube 1 plus PA 4 over 3 pi R2 cube minus PA 4 over 3 pi R cube equals to, I take here the other side, which will be equal to this time that one, R and R will cancel out, so it will be 4 gamma 4 gamma over 3. R and R are remaining with this is the 4 pi R3 square minus 4 over 3 gamma 4 pi R1 square, then minus 4 over 3 gamma times 4 pi R2 square. That's one. So on the left hand side, this P of A is times P1 plus P of A times P2 minus P of A times P3. The other side, if you leave this 4 over 3 pi, the remaining is just the area. This is the area. So I'll take outside 4 over 3 gamma. What is the remaining? Inside it is the area 3 minus area 1 plus area 3. So by looking, if you take outside the PA, V1 plus V2 minus V3. Here 4 over 3 gamma bracket A3 minus bracket plus A2. This thing is a change in volume. That means total volume initial minus the total volume final. So we have been given this to be equal to V equals to, here this is equal to total area final minus total area initial. So to look like this one, then this can be written as negative. Then area 1 plus area 2 minus area 3. So this again will be the change in total area A. So now PAV equals to minus 4 over 3 gamma times A. So you multiply by 3 PAV equals to minus 4 gamma A. Taking gamma to the other side, then 3 PAV plus 4 gamma A equals to 0, which is the required expression. Number 4. Question number 4, A, Roman 1. Explain any three properties of electric charge. Electric charge has a property number 1. They are conservative. That means the total charge of the system always, the sum of total charge of the system always equal to 0. Number 2, they are quantized. It means you cannot get a fraction of charge. Charge is a multiple of electronic charge. Therefore, it is quantized. It's a multiple of electronic charge. Another property of the charge is that electric charge I've given it almost 3. First, I said it is conserved, it is quantized, but also the property, another property of charge, apart from being conserved and quantized, is of course, there are many, but we are supposed to give 3 properties. So I'll give as we continue, because I've summarized it in the marking scheme, almost 5 of them. For Roman 2, 2 identical charges are suspended by 2 strings of equal length in air. So we have identical charge suspended in air. By 2 strings of equal length. The string make angle, this one, that means 15, then also this is 15, the total being 30. When it's suspended in a liquid of density, this one, the angle remains the same. What is the dielectric constant? Actually, if this is identical, that means this is having Q this Q, they'll try to repel each other. So if I let this is the separation distance, then considering one of the charge, the tension in the string, here will be T cosine of theta. If I take this to be theta, mass mg, and there is a electrostatic force repelling E, but also there is a component of tension T sine of theta. So when in air, for horizontal, Fe is equal to T sine of theta, question number 1. For vertical, mg is equal to T cosine of theta, question number 2. If you divide these two equations, tan of theta will be equal to Fe over mg. Fe being electrostatic force, which is equal to the charge, the first charge, Q1, Q2, but they are identical, therefore it's charge square over 4 pi epsilon radius square. This F, so if you divide it by mass, this will be mg. So this is the first equation. Tan of theta equals to Q square over 4 pi epsilon naught r square mg. So when the system is immersed in liquid, and the angle remains the same, that means this equation in the liquid, tan of theta will be equal to Q square over 4. For liquid, this will be epsilon and not epsilon naught. Epsilon, which is equal to epsilon constant or dielectric constant, K times epsilon naught. Distance square, but the weight here will be the apparent weight mg. That is the second equation. So the question here, what is mg? Where mg dash, this is the apparent weight, is equal to weight in air minus upthrust, where the upthrust is equal to weight of liquid dispersed. So it is a density of liquid dispersed times volume. But what is the volume dispersed? The volume dispersed is equal to volume of the solid, the sphere, charged sphere, which will be mass times its density of the sphere. Then we multiply by g. So this will be mg out. Then 1 minus the density of liquid over density of the sphere. Density of liquid we have been given here to be 800. So mg bracket 1 minus 800 over 160. The density of the sphere is the 160 or 1600. So just a half. So this is equal to mg over 2. So substituting it back in this equation where there is the m dash, substituting back in the m dash here, you find that the previous equation 1 and this one, they only differ in this half and this k. So On equating, you will find that 1 equals to the other side, this is the m, so it will be 2 over k if you compare the two equations. If you compare the two equations, you'll find that if you divide the two equations, tan and the tan, they give you 1. This one, you get 2 over k. So simply you can conclude from here that k is equal to 2. So the electric constant of the liquid equals to 2. We move to the next part. Roman 1, B Roman 1. Explain in the property of electric charge already. Explain 3 factors that affect the capacitance of parallel plate capacitor. Capacitance of parallel plate capacitor is given by permittivity divided by separation. So what are the factors affecting this one? First is surface area of the plates, which is direct proportional. The second is separation distance, which is inversely proportional. That means if we increase the separation, this decreases and vice versa. This is the permittivity. For air, it is 1, it is the epsilon naught, which is the epsilon naught times the relative permittivity. For air, this is 1. So this is the electric constant. Okay. If you increase this, also capacitance will increase. So those are the 3 factors which affect the capacitance. Roman 2. The capacitor of a capacitance C is the full charged by a voltage 200 battery. It then discharged through a small coil of resistance wire embedded in a thermally insulated block of specific capacity. Specific capacity equal to, this is Joule per kilogram per Kelvin. Mass of the block is 0.1 kilogram. Volt, 200 volts. Change in temperature equals to 0.4 Kelvin. What is the value of C? So we assume that the total energy stored in the capacitor equals to the heat dissipated through the block. So energy stored will be equal to heat. Energy stored, which is half capacitance times V square, equals to heat, which is MC times change in temperature. So to find C, just take MC, change in temperature, divided by voltage squared. So everything is there. 2 mass given is 0.1 specific heat capacity, and the blazing temperature 0.4, voltage is 200 square. So you get its capacitance. C, from the figure 4, find the value of capacitance C if the equivalent capacitance between A and B is 1 microfarad. So we have been given the point A here, the first capacitor C, and the point B is here. So the values of capacitors, this is the C, this is the 8 microfarad, this is the 6 microfarad, this is the 4 microfarad, and this is the 12, where this is 2 microfarad, and this is also 2 microfarad. So we needed to find the equivalent or effective resistance between, effective capacitance between point A and point B. First of all, we combine this one or this and this one in series, combine with this one in parallel to get one capacitor, combine this and this one to be in series, then this and the series, the parallel combination of this one, the final parallel and parallel, then a series with the C. So first, if you combine this and this one, 12, this will be for series, it is 6 times this one plus 6 divided by this one. So it is a 6 times 12 divided by 6 plus 12. Then this one is parallel to 4. And again, here will be 2 times, this is already in parallel. So it is just 2 plus 2 in a series with the 8. So here, what is the total? This is equal to 12 by 6, 1, 2. This is 2. 3. So 3 plus, I'm getting 4 plus plus 2 over 3, which actually is equal to 12 plus that one, 14 over 3 microfarad. The total from there to this point. Here, then series 4 parallel to this one, it is 4 times 8 over 4 plus 8, which actually, if I take, this is 2, then 2 plus 1, so is again 2 over 3. So I have from there to this 2/3 microfarad. From here to this, there are 14/3. So now what is the total from this point to this point? Total will be 14/3 plus 2/3, which is equal to 16/3 microcoulomb. So we have reduced now our circuit to 16/3 microfarad and C. So this is B, this is A. So they are already in C. This time this one it is 16/3 C plus 16/3. This total we are told equals to 1. So you multiply there of 16/3 C equals to C plus 16/3. If you take this one, if you take C in the other side, so 16/3 minus 1, C equals to 16/3. So if you multiply by 3 both sides, you can have 13, C equals to 16. So C equals to 16 divided by 13, which is 1 point something microfarad. So we move to part D. Part D, the question is, a capacitor of capacitance 3 microfarad is charged until the potential difference is 200. So V1 equals to 200 volt for C1. Another capacitor, so this C1 equal to 3 microfarad. Another capacitor was charged to a potential of 100 volts. This is having capacitance of 2 microfarad. Question number 1. What is the energy stored in each capacitor? So energy stored is equal to a half CV square. So you can calculate for capacitor 1, it is a half. C is 3 times 10 raised to negative 6 times 200 squared, you get the answer. For the second capacitor, half times 2 times 10 raised to negative 6 times 100 squared, you get the answer. So Roman 2, when the capacitors are then connected by wires of negligible resistance, so that the plates K-like charges are connected together. What is the energy stored in the combined capacitor? So it means this capacitor 1, C1, is then connected to capacitor 2. If this is positive, is connected to positive. If this is negative, connected. So this is a parallel connection. This is C2. So the question is, what is the energy? First of all, there is a common voltage which is going to be developed between the two terminals of the capacitor. So the energy final will be equal to a half times the capacitance equivalent times the common voltage square. So the task here is to find what is the common voltage, because for parallel we know capacitance, we just add the capacitors, but V. So what is important, first of all, find what was the total energy in each capacitor initially. So Q initial was the Q of the first capacitor plus Q of the second capacitor, which is equal to C1 V1 plus C2 V2. And then after connecting, the Q final is equal to Q1 dash plus Q2 dash. This time the charge in this plate is equal to C1 times V. This is equal to C2 times V. So because charge are conserved, then the total charge are equal. That means C1 V plus C2 V is equal to C1 V1 plus C2 V2. So you can find what is V is equal to C1 V1 plus C2 V2 divided by C1 plus C2. On calculating, you get this value of capacitance. That means equals to, or you can take this one back to the equation of energy. So energy stored is equal to half C total, which is C1 plus C2 bracket C1 V1 plus C2 V2 over C1 plus C2 square. So you get the total energy equal to a half C1 cancel out, C1 V1 plus C2 V2 square over C1 plus C2. So you substitute in the given data. C1 is 3 microfarad times V1, which is 200, C2 is 2 times 100 times 10, this is square times 10, negative 12 over, this is of course 5 times 10 less the 6. So you can simplify a little. This is 600, 200, you're getting 800 square divided by what you get the energy stored in the combination. That was question number 4. We move to question number 5. Yes, because of the time, let us stop here, and because we are approaching for national exam, we cannot proceed for the rest 2 questions, but the marking scheme for these questions have been uploaded in the university website, this is St. Joseph, SJUIT the rest